And we're back and better than ever, still in 19-1, where we're dealing with the definitions of acids and bases. In the first podcast, we talked about the difference between the Arrhenius definition and the Bronsted-Lowry definition of acids and bases. In this podcast, we're going to take a look at conjugate acid-base pairs. Now, what's going to happen, let me scroll down here just a little bit. What's going to happen when you put, say, ammonia in water is the hydrogen ion is going to be transferred from one species to another. In this case, the water is going to donate the hydrogen over to the ammonia. Because the water is doing the donating, the water is behaving as an acid. Now you might be saying right away, wait a minute, I thought water was neutral. It's not an acid nor a base. Well, as it turns out, the labels acid and base are simply terms of behavior. They're not absolute labels that get stuck to a compound, and that's always the way they behave. Although some acids and bases, 99.9% of the time, that is how they behave. But in reality, we're simply talking about a behavior. In this case, the ammonia is accepting the hydrogen, so that would be our Bronsted-Lowry base. So what you're left with then is when the ammonia accepts the hydrogen, remember that is a positive charge, so not only does it get the extra hydrogen, but it also takes on that positive charge. What it's left with is, or what's created anyway, is the ammonium ion. When you lose a hydrogen from water, you're just left with one hydrogen, one oxygen, and because you've lost a positive charge, it was neutral, now it's negative overall, now you have a hydroxide ion. But what can happen is the reverse reaction can also occur where the ammonium donates the hydrogen back to the hydroxide. In that case, the ammonium is behaving as the acid in the reverse reaction, and the hydroxide ion is behaving as the base. And so on both sides of the equation, you're going to have an acid and a base. Now, when ammonia behaves as a base, the product will always be ammonium. When NH3 takes on a proton, it always forms NH4+. So that pair is always seen together in a reaction. Similarly, when water behaves as an acid, it always forms hydroxide as its base. We call these conjugate pairs. This is a conjugate pair, and this is going to be a conjugate pair. And now the term conjugate simply means linked. For example, in English you have conjugate verbs where two verbs are linked together. In the biological world, bacteria will conjugate, simply meaning they will link together, swap DNA. It has absolutely nothing to do with reproduction. It's simply an invigoration of the genetic material. And so, but when those two bacteria are linked together, it's called conjugation. All right. So conjugate pairs are always seen together. Let's take a look at the next reaction and see if we can identify a conjugate pair. In this particular reaction, you start off with HCl and water, and you form ammonium and chloride. Well, how did water become ammonium? It must have accepted the hydrogen from the HCl. So therefore, the HCl is behaving as the acid, and because the water is accepting the hydrogen in this case, it's behaving as the base. So notice in the first example, water was an acid. In this case, it's a base. Again, acid-base labeling is simply a label of behavior, not necessarily what it always is. All right. In the reverse reaction, the hydronium, now by the way, this NH3 is called hydronium. That's something that's important to know. Something that might show up on a quiz. That hydronium is going to donate the hydrogen back to the chloride ion. When that occurs, the chloride will reform the HCl. Because the hydronium is doing the donating in this case, that is behaving as the acid. The chloride ion, because it's accepting the hydrogen, is behaving as the base. And so now to identify our conjugate acid-base pairs, the HCl forms Cl minus, the water forms hydronium. The only difference between two conjugate pairs is the hydrogen ion. The acid always has the extra hydrogen ion and positive charge. The base is always short one hydrogen and one positive charge. So if we go down to the next example without drawing up where the hydrogens are going, let's see if we can't identify our conjugate pairs. They are always different by just one hydrogen. So therefore, the H3PO4 is different from the H2PO4 minus by one hydrogen and one positive charge. So those two are conjugate pairs. Once again, the water and the hydronium are different by one hydrogen ion, so those are conjugate pairs. Because the H3PO4 has the extra hydrogen over the H2PO4 minus, that must be the acid, and the H2PO4 minus must be the conjugate base. Similarly, the hydronium has the extra hydrogen, so that would be the acid. The water in this case, because it's one less hydrogen, would be the base. And of course, if you want to double check that, you can always take a look at where the hydrogen's going. The hydrogen started with the H3PO4 and was donated to the water. So because the H3PO4 is donating, it's the acid. Because the water is accepting, that's the base. In the reverse reaction, the hydronium would be doing the donating, so that's behaving as the acid. The H2PO4 minus would be doing the accepting, so that would be the base. And so our idea of what the acid-base conjugate pair would be was correct. Alright, so let's go ahead and try two more here. In this particular reaction, we're taking the H2PO4. In this case, the H2PO4 is going to react with the water, and it's going to donate the hydrogen to the water to form the hydronium. Of course, here's your conjugate pair. The H2PO4 will be paired up with the HPO4 2 minus. Those are the conjugate pair in this particular reaction. But let's take a close look. Because the H2PO4 is doing the donating, that is behaving as the acid. Because the water is doing the accepting, that's behaving as the base. Now notice in the previous reaction, the H2PO4 minus was a base. Why? Because in the reverse reaction, it accepts the proton. In this reaction, it's donating the proton. If H2PO4 is the acid, the conjugate base would have one less proton and one less positive charge that goes along with that. So the HPO4 2 minus must be its conjugate base. And once again, with water behaving as a base, this must be its conjugate acid. Alright? And in this last reaction here, notice that the H2PO4 is what we're starting with, reacting with water, is forming H3PO4 and the hydroxide ion. So in order for this to happen, this guy is going to have to accept a hydrogen. So that's going to have to come from the water. So in this particular reaction, water is behaving as the acid, where the H2PO4 is now behaving as the base. In the reverse reaction, this will behave as the acid, and the hydroxide will be behaving as the conjugate, or as the base, is the conjugate base of water. So of course, these two are the conjugate pair, and these two are the conjugate pair. Alright? So, in the next podcast, we're going to take a look at what an amphoteric substance is. We're also going to practice identifying conjugate acid-base pairs in the table off to the right there. We'll see you next time.